let me know. If there's, if I'm going too fast, let me know. If whatever, if there's something that I'm doing wrong, let me know. If I'm not presenting something. Okay, so again, back to some review of what we're getting into now is another property, and this is one that's definitely going to be on our test next week, and I think it'll be on the AP test as well. So, and again, I talked about this a little bit. So this is review. I talked about this in the lesson yesterday. But vapor pressure is the pressure of a gas evaporated from a liquid. And I want to show you this short video. It's like 2 to 2.5 minutes long, but it's just, the reason I'm going to do it is because it's a good visual. So on the lesson I posted yesterday, I talked about this. I showed this, and you can see there. I like the picture on the bottom left where a vapor pressure is a property of a liquid. Even though it seems like it'd be the property of a gas, vapor pressure, it's a property of a liquid, and it's a measure of how many molecules have evaporated from the liquid to the gas. And then the picture on the right is showing dynamic equilibrium vapor pressure. So we have as many molecules going from liquid to gas, evaporating, as we do going from gas to liquid condensing. Okay, and again, I went over this already. And then I taught, and this is again, I mentioned this on the video that I had yesterday, that in first year chem and in AP chem, I'd expect you to know what vapor pressure is. Okay, vapor pressure is the pressure of evaporated molecules over a liquid. I would expect a first year chem students, and you as well, to be able to know the relationship as temperature goes up, vapor pressure goes up. And if you look on the table 10.8, which is in our book, you notice as the temperature goes up, the pressure and torr goes up. But what I wouldn't expect a first year chem student to do, but I would expect you to be able to do, is explain why. Why, when the temperature goes up, does the vapor pressure go up? And it's a really simple explanation. It kind of goes with the diagram on the right. When the temperature goes up, that means the molecules are moving faster. And if the molecules are moving faster, they're going to want to take up more space, or they're going to have enough energy to break those intermolecular forces from the liquid phase and become gas. Okay, so I'll say it again. I didn't say it very well. So as the temperature goes up, that means the molecules are moving faster. They have more kinetic energy. And so they're going to have, the molecules will have enough energy to break from the liquid phase to the gas phase. And that's why the vapor pressure goes up. Okay, and then then I talked about this page as well. And so I'm going to stop here for a second. And I'm going to show you guys, I have a short, this is like 2.5 minute long YouTube video. I think it's from a professor at the University of Texas. And he's just going to give you a visual about vapor pressure. So here we go. Can you guys see this? It looks like a tower or like a big building.
Yeah, we can see it.
I can't hear anything.
Yes, we can see it.
You can see it. Okay, thank you, Mason. Okay, here we go. So this guy, again, it's 2 minutes, 16 seconds long. It's not very long. He's just talking about vapor pressure.
You've kind of seen the results of what happens when you start studying intermolecular forces, and we start making a little bit more of a condensed phase, such as solids and liquids. You start getting all these unique properties of solids and liquids. Liquids have quite a few unique ones: viscosity, surface tension. And one of the more unique ones is vapor pressure.
Okay, so this is going to be part of what you will see on the test questions, is that, here's a couple solids or liquids or molecules. What kind of boiling point do they have? What kind of melting point? Which one's higher or lower? How about viscosity, surface tension? Vapor pressure will be one of the big ones. That's what he's going to talk about.
That's a very special case, and that's probably another thing completely. So let's just think about it. If you take water in a container and you allow it to start evaporating, the space above the surface of the water will start getting water molecules.
And I just simply like the way he gives a visual of vapor
pressures. So as that builds up, what's going to happen is these particles floating above the water can go back into the water unless they're whisked away. So if You put a lid on the container, all the particles are trapped, so the water starts going back into the water phase, or I should say the water vapor goes back.
And again, all I'm doing for those of you who are awake and listening, the whole point was simply for you guys to see. You can see, again, vapor pressure is a property of a liquid, and it's a measure of the molecules that have evaporated above water.
And as this happens, you finally reach a state at which the exiting evaporation rate equals the entering condensation rate, and you reach what we call equilibrium. So when those two rates equal, you establish a constant pressure inside your container. That pressure is called the vapor pressure of that liquid. In the case of water, you would say it's the vapor pressure of water. It's an example of what we call dynamic equilibrium, meaning when you look at the thing, you can't tell anything's happening, but in actuality, there are billions and billions of molecules leaving the surface of the water, and there's also billions and billions re-entering, and they are exactly the same rate. So there's no net change, but you have established what we call a vapor pressure. And that's hopefully a little bit more of a handle for you on what vapor.
Okay, nothing very exciting there. That's why we did jokes at the start of class. But again, a little bit of a visual there, hopefully, just to see what we're talking about. So for those of you that are awake, that's what I wanted to do there. Okay, so now back to the notes. So,
Mr. Wood, I have one question.
Yes, Mason.
Can we only measure vapor pressure if it's in a container, if the water is in a container?
Yeah, it's got to be. Yeah, it's got to be in some kind of a closed system, I think, Mason.
Okay.
You got to be able to measure it. Like this next, you guys can see this, Mason. Can you see it? It looks like some test tubes and some.
Yes, we can see it.
Yeah. Well, that is a good question, and I had to think about that one, but I'm pretty sure it's got to be a closed system, because if you don't, there's really no way to measure the pressure because you've got other things going on. So good question, and this shows that. And again, I talked about this, so we're still kind of reviewing, but this shows that if you look at the diagram at the top, we've got a vacuum on the left, and then we got water. Water has two hydrogen bonds. And then we have C2H5OH, that's ethyl alcohol. That has one hydrogen bond and a London force. So it's not quite as strong as intermolecular force. And notice it has a higher vapor pressure. So the relationship here is intermolecular force goes up, vapor pressure goes down. Intermolecular force goes up, vapor pressure goes down. And then the one on the right, the C2H5 2O, that's called dimethyl ether, and that is going to be a dipole, which is the weakest, so it has a higher intermolecular force. Let me just real quick, and again, I think I talked about this in my lesson that I posted. But if I diagram these, so if I come over here, so water, so what we're doing is we're comparing intermolecular forces. So water is like this. So water has two hydrogen bonds. So that means that's held together. That's pretty strong intermolecular force. Remember, we said ionic was number one, hydrogen bonding was number two. Well, then the ethyl alcohol looks like this. This is the one in the middle. So this is the C2H5OH. Well, this one has a hydrogen bond too, but there's only one hydrogen bond, and then there's a lot of its London. So this has a hydrogen bond, but it's also got a lot of London dispersion forces. That means water has a stronger intermolecular force. It's held together tighter, so not as many molecules are going to evaporate. Okay, and then the other one there was called dimethyl ether. It is C2H5. C2H520, and it looks like this. And again, this is kind of some organic molecules, which, like I said, hopefully by then we'll be back full, but who knows what will be going on. But it looks like this, and because oxygen was going to take the shape bend, this is going to be a dipole. But of those three, this one has, of these three, this, and this has the weakest intermolecular force, and so it's going to have the highest vapor pressure. So what we're saying here, as the intermolecular force goes up, the vapor pressure goes down. As the intermolecular force goes up, the vapor pressure goes down. Okay, so again, all that is I'm repeating myself, but I did want to go over that because it's vapor pressure is definitely something I bet we'll see on the AP test. I know we're going to see on our test next week. Okay, so then continuing that. Okay, so low vapor pressures low vapor pressures, that means not very many molecules are evaporating, have a high molecular weight, so they're going to have a more polarizable, and they have a strong intermolecular bonding. So again, as the intermolecular force goes up, the intermolecular force goes up, the vapor pressures go down. Okay, and this is something I'm going to skip over, but if you guys, again, take chemistry beyond our class, you're going to get into this. This is a kind of an adjustment that is made vapor pressure with temperature, but it's not going to be part of our class, so we are just going to skip over this. But we're going to do this page. Okay, so solid or liquid to gas and gas to liquid, and the heat of vaporization. So I'm going to give you guys a minute to copy this down. Okay, so going liquid to gas is boiling. I'm going to wait here one more second. So if you guys, one thing I don't have written down here that would be good to know, and I haven't, and it's an important point to make, but a change of state. So that means going solid to liquid or liquid to gas, or you could really go solid to gas or gas to liquid. A change of state is breaking intermolecular bonds, not breaking intramolecular bonds. So a change in state is breaking intermolecular bonds, not intramolecular bonds. And so when we're going liquid to gas, what we're doing is we're breaking intermolecular bonds, and we're going gas to liquid, we're actually forming intermolecular bonds. But going liquid to gas is boiling or evaporating, and that is an endothermic process. Boiling is an endothermic process. It takes energy to get a liquid to a gas, and a gas to a liquid is condensation, and so that's going to be a exothermic process. So it's going to be given energy is going to be given off, and yes.
In ionization, then what happens to the intramolecular bonds?
In what's that? Say it again, David.
Ionization, when it goes from a gas to a plasma.
That when it goes from gas to plasma, that would again be endothermic.
But what would happen to the intramolecular bonds? Would they stay on?
They would. Well, what happens there is, I think what happens, David, and I'm not the great understanding, but what happens is the gas, the electrons are taken away from the gas, and the gas gets ionized, and so it takes energy to do that. To take the electrons that are outside the nucleus, but to remove those electrons to leave a positive ion, it takes energy to do that. That's my understanding. But when we're going solid to liquid, liquid to gas, or gas to plasma, like you said, all those would be endothermic. You'd have to put energy in. Does that make sense? Think about it.
Yep.
It takes energy to do it, and then the other way will be exothermic because bonds will form. Okay, I'm not going to make you memorize these heat of vaporizations, but if we go back and we look at these, this is the kind of thing, okay, in AP Chem. So we got water, argon, ethanol, and mercury. So I'm actually gonna minimize this and write on the board here. Okay, so here's going to be another one of those things that we're going to have. So again, beyond AP Chem. Okay, so we got to know what is the heat of vaporization, and I haven't defined it here, and it would be good to know this. And by the name, you can probably get it. The heat of vaporization is the energy required to evaporate. Technically, here there's moles to evaporate 1 mole of substance. The heat of vaporization is the energy required to evaporate 1 mole of a substance. Okay, so you need to know that. That's what's going on. We're talking about going from a liquid to a gas. So the energy to convert 1 mole of a liquid to 1 mole of a gas of a substance. Well, here's what we got. So here's the delta HV. This is the heat of vaporization. So water is 40.79 kilojoules per mole. Argon is 6.3 kilojoules per mole. Ethanol, and what ethanol is, I actually just had it on the board. It's C2H5OH. It is 39.3 kilojoules per mole. And then mercury is 59.0 kilojoules per mole. So here's the kind of thing that I'm going to ask you in AP Chem. Okay, so in first year Chem, I wanted to know what heat of vaporization is. We're going to do a simple little calculation with it here in a second. That I will expect you to do too. But here, I want you to explain, why did they fall like they did? Why did they fall like they do? This one is the most. Why does mercury have the highest heat of vaporization? Well, the explanation is this is a metal. Mercury is a metal. And it has very strong cohesive forces. Now that one probably be a little bit harder to do, but you could identify this as a metal. Okay, and that means it's got, just like I went over earlier in class, it's sea of electrons. It's held together pretty tight. Okay, then I've got number 2 is water. Why would water be the second in this list? Well, water has 2 hydrogen bonds. That's pretty strong. It's a pretty strong intermolecular force, so it's going to take more energy to. That means water is clinging to other waters. Water is holding real tightly to other waters. It's going to take more energy to break it. Ethanol is number 3. Why is ethanol number 3? Well, this has 1 hydrogen bond and then a bunch of London dispersion forces. Well, that again, and you can see these are pretty close to the same, but water's a little bit more because it's got 2 hydrogen bonds. And then argon, this is the weakest, and this is a noble gas, so it's nonpolar, so it's held together by London forces. So what I'm trying to point out to you here, okay, so in AP Chem, okay, well, here's the list. What does this mean? Why is this the highest? Why is this the lowest? So what we're seeing here, that as the intermolecular force increases, the heat of vaporization increases. So there's a lot of relationship here with intermolecular force that you've got to know. But to me, and of course I've taught this for a long time, but that makes sense. If something's held together real tight, it's going to take a lot of energy to break it apart. Okay. So how heat of vaporization works. And just its connection to intermolecular forces. Can you see that, Kara and Mason?
Yeah, we can see it.
Okay. So here's the next page. One thing, and I don't know, I did this in my class in first year Chem, and your teacher might have done it too. But to get a liquid to boil when it's not, and I might even do this on Thursday, maybe I will on Thursday. I'll get out the vacuum pump, but it's possible to get a liquid to boil without heating it. And that's what this is about. liquids boil when the atmospheric pressure equals the vapor pressure. So now you know what vapor pressure is, okay? It's the pressure above a liquid. So when the air pressure equals the vapor pressure over a liquid, the liquid will boil. And I'm not going to hold you to the boiling and evaporation. It's kind of interesting when you look at this table here. Look at those boiling temperatures. The column on the right, Mount Everest, of course, the highest place on the planet. The water boils at 70 degrees. Mount McKinley, the highest mountain on the North America, 79. Leadville, Colorado, the highest city in Colorado, water boils at 89. So as the elevation goes up, the boiling point goes down because you don't reach that point. And I think I'll try and do this on Thursday, where I'll, as best I can on a Google Meet, I'll show you. I'll try and get ice water to boil without heating it. And I'm going to use that principle. Okay, so we talked about liquid to gas, gas to liquid. Now we'll talk about, or now here's a little calculation. So I'm going to give you guys a minute, read that, and see if you can do that problem. Calculate the energy required to boil 25 grams of liquid 100 degrees Celsius water, changing it to 100 degrees Celsius gas water. So here now we're doing the energy. Now you have to be given the units, or you have to be given the constant here. So that technically, when it says when steam condenses back to liquid, that is the heat effusion of ice. Okay, look, follow the units here. I'll give you a minute, see if you can do it. And again, I always kind of think following the units is a really good thing to do in our class. And whenever you bog down on a problem, following the units. Okay, so if I do this problem again, follow the units. So if I have 25 grams of liquid water, and I'm told that it's 40.79 kilojoules per mole. That is the energy involved in this change of state, which means I need to get, since this is moles, I got to get the grams into moles. And since this is water, so I'm going to put grams in moles. So here we go, going back, following the units. 1 mole, and for water, the molar mass is 18. So 18. Now I can use this number. So now for every 1 mole, again, so that cancels out 40.79 kilojoules. Again, I want to talk about doing some calculations of change of state, and I'll get to that either today or maybe tomorrow in the lesson. But it's really just following the units. So then if I multiply and divide everything out here, I had 56.7 kilojoules. I can't remember, was it 25 or 25.0? My sig figs, if it was 25, that should have been 57. So again, follow the units, really, not a bad problem for you guys to have done. You okay with there? Okay, now let me just kind of talk about phase changes. So if we have solid and then we have gas on a continuum, liquid is way down, way closer to here. in terms of energy. We're looking at this in terms of energy. So what we were just talking about, okay, going here to here, that's it, going liquid to gas, that's evaporating. And going this way, going from a gas to a liquid, that's condensation. Okay, so here in a second, we're going to talk about solid to liquid, and of course, that's melting. And going liquid to solid is freezing. I guess back east, my oldest son and daughter-in-law and two grandsons live in Philadelphia, and it sounds like they're getting a big snowstorm. So they have a lot of freezing, where we are having a nice day. So going this way, and what David asked about earlier, which was a great question, I probably didn't answer very good. Plasma's out here. I mean, it's way out here. It'd be way out there. And Bose-Einstein condensate would be way over here. But we're just going to talk about what we experience. But going this way, solid to liquid to gas, that's always going to be an endothermic process. We're always going to have to put energy in to do that. And going this way is going to be exothermic. And remember we said to break bonds, which we're doing solid to liquid, liquid to gas, we're really breaking remember, in phase changes, we're always breaking intermolecular bonds. In phase changes, we're always breaking intermolecular bonds. But in this diagram going this way, solid to liquid, liquid to gas is endothermic, and going gas to liquid, liquid to solid is exothermic. Okay, and it's just to kind of see what is going on here, and also to kind of just see where these fit in the continuum. Okay, so then back to the notes. Okay, so the next slide is going to kind of continue this. Okay, so here we go. Solid to liquid. And I never understood why they called melting heat diffusion, and I should know that, but I don't know what it is. But there's an explanation for that. Okay, so I'm going to pull this down, and I'll tell you what, I'm going to leave that up for just one more second. So the heat of fusion, which you're going to need to know, heat of vaporization makes a lot of sense. So it's the heat required to take a liquid, 1 mole of a liquid to a gas. But the heat of fusion is the energy required to change 1 mole of a solid to 1 mole of a liquid. And then freezing is the opposite. But so the heat of fusion, and we have these values. So again, in our class, it's expected, okay, know what that means. What does the heat of fusion mean? Okay, the heat required to melt 1 mole, and that doesn't make as much sense as the heat of vaporization. So you need to know that. But here are the numbers that were given to us. So heat of fusion is indicated delta HF, or just HF. So we have water, carbon tetrachloride, and sodium chloride. Okay, well now here again, now in AP Chem, it's like, okay, why? Why is this one the strongest? Why does this have the highest value for the heat of fusion. Why does sodium chloride take the most energy to melt? Well, let's go back and put it into a group of intermolecular force. Sodium chloride, okay, and I could ask you, okay, think about it if you're awake and following along. Some of you are, some of you are in the middle of a great video game or sleeping, but what category does this go under? Sodium chloride. Ferris Bueller's teacher, anybody? 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 What kind of intermolecular force is this? Sodium and metal, chlorine and nonmetal.
Ionic.
This is ionic, right? Somebody said it good. That means that's the strongest one, right? I said ionic is the strongest intermolecular force. Well, it's going to take the most energy. And again, if you think about it here on a beautiful Tuesday morning on Groundhog Day, that makes sense. It takes a lot of energy to melt that. The second one is water. Like we said, this has hydrogen bonding in it. So that's a pretty strong intermolecular force as well. Well, it's got to, again, not anywhere near as close as strong as ionic, but it's got a strong intermolecular force. And then carbon tetrachloride. Now here we go back to what we were doing way back even in first year chem. Carbon tetrachloride, could you write the formula for that? What would be the formula for carbon tetrachloride?
CCl5.
CCl, close.
4.
And CCl4. Tetra's 4. So CCl4. So now we go back to chapter 8 and 9. What would be the shape of that? Well, if I do the dot structure, it looks like this. So it's got 4 electron domains. What's the shape of this? And again, you may not, maybe you haven't worked on those, but by next Wednesday or Thursday, you need to have that in your brain. This is tetrahedral. And the tetrahedral shape is nonpolar. It's got the same elements out here. So this is nonpolar, which means this is London dispersion forces. Okay, so here again in AP Chem, well now, why sodium chloride has the strongest heat of fusion? Because the relationship there is the intermolecular force is higher, the heat of fusion is higher. The intermolecular force is higher, the heat of fusion is higher. Okay, and again, if you think about it, that makes sense. It takes more energy to take a mole and to break those bonds in the heat of fusion. So just like heat of vaporization, it's really the same exact pattern there. Okay, I'm going to skip a couple pages here. Okay, so back to the notes. Like I said, I'm going to skip a couple pages. Okay, I'm just going to go through this. Okay, and then something just to know the definitions. Is solid to vapor is sublimation, and then vapor to solid is deposition. So a great example of sublimation, a great example of that is dry ice. Dry ice goes straight from a solid, it skips the liquid phase, and it goes straight to vapor. And deposition is the opposite. And to be honest with you, I need to have a good example of that, and I don't have one of deposition. But that's solid to vapor, sublimation. Another good example that you guys probably remember, but you don't have these in your home, but we had ice cube trays, and maybe you do, but you put water in the ice cube tray and then you put it in the freezer, and then in a day or two it's frozen. But if you let it sit in there for months and months at a time, sublimation would occur and some of the water would literally evaporate away. Okay, and I want to just kind of get started on this problem, and then I'm going to finish it because we're going to run out of time. But I do want to start on this, and then I'll finish this. But the heating curve for water. So let me put this all up, and I'll kind of talk about it, and then we'll stop there. And then tomorrow, probably for the lesson, what I'm going to do is I'm going to go over this. I'm going to do this problem at the bottom. And it kind of looks like steps. So the heating cooling curve for water, and there are some problems here. And again, tomorrow we won't Google Meet, but tomorrow we will. I'll probably do this problem is what I'll probably do for tomorrow. And there's one other thing I want to talk about. I'll get into, and then we'll finish the chapter, do questions. And if we're not going to do chapter 11, we may even dip into chapter 12, which would be good. We just need to keep moving. Okay, so I'm going to minimize this, and again, I'm going to come back and do this for our Google Meet tomorrow. But this diagram, and actually doing this problem, it always to me kind of makes sense if I follow the diagram. So heating cooling curve kind of looks like this. This goes up, flattens out, goes up, flattens out, goes up. And this is a heating cooling curve, and it's usually for water, but the way this works is down here is when it's all a solid. And at this point here, I'm going to get a different color. At this point, this is when we're going to use the specific heat of the solid, of ice. That's where we're going to use the specific heat of ice. And again, I'm going to do that problem that I have on there. Okay, so then here, so first of all, think about it. Again, we come from where it gets cold in the winter some days, and so when we have it all solid, well, if we heat it, what's on each axis, so if we heat it, eventually we're going to get to where it's completely all the solid is gone. And so here, whenever the graph is flat, there's a change of state. So here we're going solid, S to L, we're going solid to liquid. Okay, that's what's going on here. And so this is where we use the heat of fusion. And again, I'm going to do a problem. In first year chem, we really just work from here to here. And not that it's difficult, and we could have really in first year chem, we could have done here and here. But that's usually what we did. So we took pure solid, we melted it, and when a change of state is occurring, the temperature doesn't change. When the change of state is occurring, like here is going to be liquid to gas, there's no temperature change. Okay, and then up here is when it's all liquid. It's all liquid, and this is where we're going to use the specific heat of the liquid. For the problem I'm going to do of water. So when the graph is sloping up, then we have one state. But when the graph flattens out, then we are going through a change of state. So we start out just all solid, then we melt the solid to where it's all liquid, and then we heat it. We continue to heat it. And so we get here, we go liquid to gas. So that's boiling. That's evaporating. And so this is where we're going to use HV. That's where we're going to use the heat of vaporization. Okay, and then finally, we get up here is when it's all gas. And so this is where we're going to use the specific heat of the gas, or in the problem that I'm going to do, steam. Okay, and again, in first year chem, we just really work from here to here. But in our class, we're going to work all the way. We're going to do like 5 steps. The quiz, I think on the quiz for chapter 10, it is question number 4. And so what I'm going to do for the lesson for tomorrow, and I'm going to sign off here, I'm going to do that problem I had in the notes. And it would be good before we meet again on Thursday, maybe to try that number 4 on the quiz, and we can look at it and make sure we're good with that. Okay, I'm going to stop there. Any questions you guys have? Okay, Tay, time to wake up now. Hey, some of you guys, it's time to wake up. Okay, everybody else, tomorrow I'll have a lesson posted. And then, again, keep the Tinker Toy Labs for right now. We'll see what the school board decides tonight. So if that's it,
Thank you so much.
I will see you guys Thursday.
Thank you.
Thanks, Mr. Wood.
Thank you.
I'll see you for Google Meet a little later today. We'll work on that stuff. Okay, Allie, I didn't get your quiz.
Okay, so basically you emailed me back saying that you didn't have my quiz on the chain that had my lab on it. So I think when I responded, you just saw that first email that had my lab. I attached the photos of the quiz.
Okay.
So you can either
So it's in
look
that
down.
same line. You didn't send me anything back then today?
Well, so this morning I did email you the pictures again, and then I also started a new email chain with the pictures so that it might be easier for you to see.
Okay.
But either way, they are both, they're there. So just let me know when you have it, okay?
I'll do that, Allie. I'm going to do that.
Thank you.
See you, girl. See you.
Have a good one.
Bye. Dave,
Mr.
okay?
Did you see my quiz?
Let me see. Yeah, while you're here, if I don't have it, I can check, David. Did you send it? I don't have it yet. Did you send it to me this morning or?
No, I thought I did a few days ago.
Just 1 second. Let me check. Sometimes all these emails, I hope they decide you guys can come back. What do you think?
I really badly want to go back in person.
You want to come back in person, David?
Yeah, so bad.
Man, I don't know if I see it. Could you just send it to me again, David?
Okay.
I don't know why. I don't know.
And also the Tinker Toy, do you want me to send that or should I just hold on to that?
No, don't send that. Just keep that like I said. Wait, just a second here. Just a second.
Also, are you gonna go to FCA this week, Mr. Wood?
How did that go? Did you get all that stuff? Whoops.
It went pretty good actually. We had a good discussion on Romans 1.
Good. Yeah, I ended up, I just had work to do and I just was here and I had some Google Meets and I just wasn't able.
How was Texas?
How was what?
Texas.
Texas was good. My son, he was ranked 6th and he ended up 6th, so he got where he started. So he was disappointed, but I thought it was fun. I enjoyed it. I'd never been to Austin, Texas. So
cool. So
yeah, if you can send me the quiz, David, just here whenever you get a chance later today. And if I don't get it, I'll email you. And then, but keep the Tinker Toy Lab for right now.
All right. Thank you so much, Mr. Woods. Have a good rest of your day.
You too, David. Bye.
Bye.